Can we make it just one slide at a time? Yeah, okay.
No.
Yeah. Okay.
Okay, sorry.
Okay, can you hear me? Also in the back there? Louder? Like this? Can you hear me now? No? Yes? Okay. So thanks, Samuel, for the introduction, and thanks, Feliciano, for louder even. Zoom max. Okay. Now, better? No? No. Now? Okay, okay. Too much? No, okay. Sorry for the inconvenience. So thanks, Samuel, for the introduction. Thanks, Feliciano, for inviting me here. And thanks to all the organizers for putting together these beautiful summer schools. I'm very excited to be here. So today I would like to talk about Wannier function, the Wannier function software ecosystems for material simulations. And essentially what I would like to do today is to, on the one hand, share with you what are the major applications of Wannier functions in terms of material simulations and properties of materials you can calculate thanks to Wannier functions. And I would like really to give you a very broad and quick overview of many different properties. And on the other hand, to slowly guide you through the more practical aspects of constructing Wannier function and present you the Wannier 90 code for maximum localized Wannier functions and many other kinds of Wannier functions. We will see that, so that we slowly move into a practical mode, and we will have a hands-on tutorial after lecture of Feliciano at I think it's going to be at 11. Okay. So let's see if this works. Yeah, so I won't actually give you again another introduction to Wannier function. This has been done by Nicola Marzari yesterday in his lecture, but I will give you a quick recap of the major and the most important concepts, just to refresh a bit these concepts and to set the notation. So if you remember, Nicola showed to you that the key concept behind Wannier function is the gauge freedom. So what we are doing here is essentially a Fourier transform from block states in reciprocal space to these Wannier functions in real space. And the key aspect is that you have a freedom in choosing the gauge. Okay, so you have a phase factor in front of your block state that you can change. And this would be for one isolated band. For instance, these bands here that I'm highlighting with a blue rectangular. And if you have multiple bands, so you have composite bands. Yes. Okay, so if you have composite bands, you even have more freedom because there is an entire unitary rotation that you can choose in different ways, and you will still get these different kinds of Wannier function. Sorry, there's no. Okay. Can I?
Yeah.
Okay. Okay, as Nicola has shown to you, all these Wannier functions have interesting properties. They are orthogonal, they span the same space of the initial block states, and they are periodic in the supercell. But different choices for this unitary matrix actually result in different localization properties of any function, okay? So the key aspect here is how to choose the unitary rotation, and there are many recipes available today. I will show some of them, but the most popular, the most important one is the maximum localization that has been introduced by Nicola yesterday to you, okay? So the idea is that we choose the unitary matrices in order to minimize the quadratic spread of the position operator. And once you do this, you get the most localized Wannier functions that are possible, okay? So in practice, you have your block state from calculated the same quantum espresso, your favorite ab initio electronic structure code, and you refine, so with an iterative procedure, you optimize this unitary matrix until you minimize this omega spread function, and then you have your Wannier function, okay? So in practice, and this has been, again, discussed by Nicola yesterday, but just to refresh a bit the concept, this amounts to project your block states onto some localized orbitals, could be SPD, SPD3 hybrid orbitals. And this will be essentially a way to find an initial gauge and also an initial subspace in case of disentanglement. We'll see that in the next slide. And once you do this, you have to start the iterative minimization of the spread function, okay? So you follow the gradient, essentially, and until you get to the smallest value for this omega spread function, okay? So what you actually need are the overlap matrices, and this is, again, what we discussed in Nicola, but you also need this initial projection function. Nowadays, there are methods that try to calculate this initial gauge and also initial subspace without resorting to atomic orbitals and to chemical intuitions, but more to, let's say, linear algebra concepts. And one of these is the selected column of the density matrix approach that we'll quickly present later on, okay? So maximum localizable function would give you the, let's say, Wannier function for the red bands here, so for composite bands, okay? So, but you can also do this for in a more general case, when you have entangled bands. This would amount, for instance, to try to get Wannier functions for the green bands here, or for the red bands plus the green bands, okay? And this problem is essentially about extracting a manifold that is differentiable and has optimal smoothness. And again, you have seen yesterday that the key concept here is to minimize the spillage between manifolds and neighboring K points, okay? So you want to essentially follow the orbital character of your bands, and this is called disentanglement that was introduced by Hugo Sousa, Nicola Mazzari, David Vanderby more than 20 years ago. So you minimize this spillage, okay? You do this over the entire Brillouin zone, and you disentangle a manifold. And then once you have done this, you can proceed with the usual maximal localization procedure and minimize the gauge-dependent part of the spread, okay? So essentially, you have two unitary matrices, and the product of these two unitary matrices is the overall unitary transformation that brings you from your block state to your Wannier gauge. And Nicola has shown to you the example of silicon. So if you do separate valence bands and conduction bands of silicon, you get the bonding, anti-bonding orbitals that you see here. And instead, if you do all the 4 valence plus 4 conduction bands together, you get sp3-like orbitals, okay? So in a nutshell, and this is really my last slide of recap, what you want is good localization in real space, and this translates in reciprocal space as trying to have the smoothest gauge that is possible, okay? So remember, you know, if a Wannier function is localized in real space, this means that the gauge you have in reciprocal is smooth and vice versa, okay? This is very fundamental concept. And as we said, you know, you start with a ground state electronic structure calculation, let's say quantum espresso. You choose a subspace typically with these projection functions, and find a unit transformation by minimizing this omega spread function, and then you get this Wannier function in real space. So these are really the, you know, if you have to remember one equation, this is probably what you want to remember, the definition of Wannier function in terms of Fourier transform, and this D matrix, unitary matrix here that represents the optimal unitary rotation that in the maximal localized recipe is chosen as to minimize this omega function, okay? Good, so let's go a little bit more, let's do some examples. This is a very simple toy example. This is a carbon chain with 2 atoms per unit cells, and it's a dimer, so the distance between the 2 carbon atoms is, the distances are not exactly the same. And you know, if you have 2 green bands here, band number 1 and band number 2, and you can calculate maximum localized Wannier function for these 2 bands, okay? And if you do that, and this is the result of an actual calculation, and I want to thank Giovanni Pizzi, who basically prepared this picture, you get this yellow Wannier function that are essentially centered in the middle of the bonds, okay? Now, let's say we make this toy example a little bit more challenging, and we try to disentangle this green plus red bands, okay? So now we have band 1, band 2, band 3, band 4, but also this higher band that goes, you know, up to 10 and 12, say, has contribution coming from the bands 10, 12 up there as we go closer to the gamma point, okay? So, and this, what you see here on the left-hand side is actually how the unitary matrix that you get from disentanglement looks like, okay? So you see that the first 4 bands are entirely included, okay? But then the disentanglement is capable to mix only the states that you really want to extract. And in this case, this means the states with p-like orbital character, okay? So The resulting Wannier function that you get for this carbon chain would be exactly these four p-like orbitals. Okay, so let's say the direction of the chain is x, you get py and pz orbitals, and they are centered on the carbon atoms. Okay, so this is a toy model if you want, but it's useful because you can visualize what is actually happening under the hood when you invoke the disentanglement procedure, when you invoke the maximum realization. But so coming back to my title, what are the major applications of this Wannier function? So the first application, I call it the zeroth application, is the one that has been already discussed by Nicola, and is about understanding and characterizing chemical bonding. And I won't talk too much about this. I will focus more on I would say, practical application, or let's say less different kinds of application with respect to just understanding chemical bonding. And the most popular, and the reason why basically we are here discussing Wannier function in this workshop, is reciprocal space interpolation. This will be the focus of probably my talk, and also the focus of let's say how Wannier functions will play a role in this semester. Okay. And then there is another interesting and wide area of application for Wannier function, and this has also been touched upon by Nicola yesterday, and it has to do with the quantum geometry and topology of the electronic structure. Okay, so there are a number of quantities, very important quantities, like polarization, so electronic polarization, orbital magnetization, topological invariance, and many, many more. I will make some examples that are fundamentally connected with the concepts and the theory of Wannier function. Okay. And so here we're not just talking about interpolating these quantities. Really, this has to do with the very definitions and derivation of these concepts. Okay, and then there is a third class of application, which I think is no less important, that has to do with advanced electronic structure methods. Okay, so often when you want to go beyond density functional theory, okay, and one example would be dynamic and field theory. I will make another example related to Koopman's functionals. You really need to have a formulation that is based on localized orbitals in real space. Okay, and here Wannier functions actually play a major role. So you see this picture here that is borrowed from a review article that we are putting together, and that I will come back to this review because I think it's useful for for basically all of the participants of the school. But this picture that I borrowed from this review shows a little bit what is the idea here. No, so you start from your ab initio calculation. Let's say with quantum espresso, you Wannierize, you get Wannier functions, okay, and there are different minimization methods you can use. And then you build essentially a ab initio type bonding model that allows you to interpolate different kinds of quantities, okay? We will see examples of that. And once you've done this, you get access to a number of simulations, okay, a number of properties ranging from ballistic transport, nanostructures, to baryology, so all these quantities related to the Berry phase, to topological invariance, and related properties, to electron-Phonon interactions, which is the key core topic of the school, and to these beyond DFT approaches. Okay, so what are we doing here? Basically, you see, Paolo has given you an introduction to quantum espresso. This will be your ab initio engine in this more general scheme. Today, and yes, so yesterday, Nicola, today myself and Junfeng Zhao and Jemo Lim will give you. We will give you basically an introduction to Wannier functions and how to get Wannier function with Wannier 90, but also to these more advanced minimization methods that go that either help you to solve the problem of finding Wannier functions, or as in the case of Jemo Lim, to use Wannier functions in a more sophisticated way to do perturbation theory. Okay, and so this will be the topics that Junfeng and Jemo will discuss on Saturday. Okay, but a point that I would like to make is that this Wannier interpolation is not just for DFT. It's actually even more useful when you go beyond DFT. And there are a number of lectures in the school by Stephen Louis, by Lee, Delben, and many others that are about GW and related calculations. And there, the interpolation that Wannier function can provide is actually very, very useful. Okay, so you can interpolate GW structures more or less as you interpolate DFT structures. Okay. And then, of course, there is electron-Phonon interaction, which is the key sort of topic of the school. And there all these lectures by Feliciano, Agostino, Roxana Margina, and Samuel Poussin and others will use Wannier interpolation to calculate electron-Phonon coupling related properties. Okay. So why I'm using this term Wannier engines, okay? Because in the end, what you will see today is a single code, which is called Wannier 90. But the point I would like to make here today is that what I show is somehow more general, okay? So in principle, you can have different codes. So Wannier engine for me is a code to obtain localized Wannier functions and related properties. And the most popular is Wannier 90, and this is what we're going to see in the hands-on tutorial. But there are other engines available these days. One is the atomic simulation environment. Another one is the Julia Wannier code that has been written by Feng Chao, who's here in the audience and will give you a lecture on Saturday. Okay, so it's an engine in the sense that you use it to get Wannier functions. But then, of course, this is part of an ecosystem. So there's an entire set of other packages that are connected to Wannier 90. So I think the most modern way to look at this code is as a center of a more wide and broad software ecosystem. So on the one hand, on one side you have these initial engines, and one of this is Quantum Espresso. But as Nicola has mentioned yesterday, there are very many codes, first principle codes that have an interface with Wannier 90, and then on the other side of this ecosystem, you have all these other codes that calculate specific properties of materials, okay? And this can range from GW calculation, transport calculations, electron-phonon coupling, optics, and much more, okay? Let's start to discuss a bit more in detail the code. So this is your probably best entry point to Wannier 90, is the official website. You can download the code, which is written in Fortran, and it's open source. There is also a GitHub page, okay, where the code is hosted. You get also the developed version of the code, not just the latest release. There is a very well done user guide that you can download as a PDF from the website. But actually, recently we also created an online version of the user guide, which is going to replace the PDF version and is fully searchable. Okay, so I think I would really encourage you to experiment with that, because at some point this will be probably the main user guide. There are also tutorials. I think there are more than 30 of them covering most of the features of the code. And for the core features, there are also solutions to these tutorials. Okay, so I think this is a great resource for all the users. There is a community email forum. You can subscribe to that. And of course, there are some key publications discussing the features of the code. Okay. And of course, if you use the code, I mean, it would be nice to consider mentioning this, the key publication that you find on the website. This was, of course, an effort started, I would say, almost 30 years ago by Nicola Marzari here, and David Vanderby, and then Ivo Souza, and then after that, Arash Mostofi, Jonathan Yates, Joanny Pitzing, and others. But I think today, this is more a community effort. Okay, so if you look at the latest article discussing the features of Wannier 90, you see there's a long list of authors. Okay, in fact, over the last few years, the code has transitioned to a community code. So this is a community effort, and one key event that triggered this was the coding week we had in San Sebastian. This was in 2016, so 8 years ago, and this was the occasion where the Wannier 90 code went on GitHub. And if you see here the number of commits, actually, as a function of time, you see that after this simple thing of moving the code to GitHub and opening the development to the wider community, the number of contributions has really increased a lot. Okay, so in fact, I really encourage you to actually go to the GitHub page and not just be a user, but also be a contributor. This can mean also improving the documentation, finding bugs and reporting bugs, adding new features, and contributing these features back to the main code. Okay. What are the features of the code? Of course, you find the fundamental algorithms related to Wannier function. You find the Nicola's maximal localization algorithm. You find the disentanglement by Ivo Souza, Nicola Mazzari, and David Vanderby. But you also find some more recent developments. Some of these I will mention in a moment. They're related to symmetry adapted Wannier functions, so enforcing some degree of symmetry in the Wannier functions you get. A very recent implementation, well, not, it has a couple of years, or 3-4 years by now, but we have a more recent implementation of this SCDM method that I mentioned to essentially define initial projections without having to resort to chemical intuitions. And there are a number of interesting features that you find here. The code actually has been ported to MPI parallelization. And there are also post-processing features, okay? So you can, of course, you can interpolate GW structures, as I mentioned already, but you can also calculate Berry phase properties like Berry curvature, orbital organizations, and more. There are routines for transport, and especially Boltzmann transport and ballistic transport. But my message here is that more and more additional features related to post-processing will actually be implemented in external packages, okay? So there are dedicated packages to the different kinds of properties you can calculate, okay? So more and more you will find some of this being developed in codes of this wider ecosystem, okay? Okay, so we have discussed very briefly what is Wannier 90, and now we are, we really have to discuss what is this Wannier interpolation, because it is the main reason why we are discussing Wannier functions in the school. And so in a nutshell, Wannier interpolation is similar to Fourier interpolation. So you have if you remember, some of you have studied a little bit of signal processing. Whenever you have a signal, if your Fourier transform of your signal has a finite bandwidth, okay, and you sample the signal with a sampling rate that is at least twice the bandwidth, okay, and this is called the Nyquist-Shannon condition. If you do that, you can reconstruct your signal exactly, okay, with no loss of information. So from a discrete sampling, you can reconstruct exactly the entire signal. And if you want, Wannier interpolation is basically the same thing, but in the context of electronic structure calculation, okay? So the idea is that you have your k-space quantity. For the sake of concreteness, let's think this is the Hamiltonian. And you express it as in terms of Wannier functions, okay, in a Wannier function basis. And this is like doing a Fourier transform to real space. Now, the interesting aspect here is that these Wannier functions are exponentially localized, okay? So even these matrix elements of your Hamiltonian are exponentially localized. And so what happens is that if you try to calculate this on denser and denser grids, this corresponds to having a Wannier function representation in real space with longer and longer, so with matrix elements between Wannier functions that are farther and farther one from each other, okay? But because these are exponentially localized, at some point these matrix elements starts to be zero, okay? So there is no point in doing this Wannierization on a very, very dense grid, because you simply add zeros to your representation in a real space, okay? So this is why with a dense grid, you can have, exactly represent your Hamiltonian in real space through Wannier functions. And once you do a reverse Fourier transform, so you go back to reciprocal space, you can reconstruct your Hamiltonian at an arbitrary k point in reciprocal space exactly, okay, with no loss of accuracy again. So you see, there is a first Fourier transform where you have your epsilon that are your, let's say, DFT Cohen-Sham eigenvalues. There are these unitary rotations, V and V star. And then there is just a Fourier transform. And once you Fourier transform X, you get this slightly more complex formula. We'll comment that in my next slide, but this is essentially just a Fourier transform. And you get your Hamiltonian at an arbitrary k point in the Wannier gauge. So the last step to get your interpolated structures, in this case, because we are considering the electronic structure, the electronic Hamiltonian, the last step is just to diagonalize this matrix, because this is still in the Wannier gauge. So you diagonalize that, and you get your Hamiltonian gauge. So you get your band structure. Okay, so your Hamiltonian eigenvalues. Okay, so if you see, this formula here is slightly more complex than a simple Fourier transform, and the reason is because you have to take into account that when you have a matrix elements between Wannier functions in real space, your closest partner might sit actually in a neighboring supercell. Okay, and so you could use a simple Fourier transform, and if you this would basically mean using the Bonfort-Karman supercell, but this is actually wrong in the limit of gamma only sampling, and even with finite k point sampling, it would require much denser grids. Okay, while this formula is slightly more sophisticated, we call it minimal distance Lepika selection. It just takes into account that, again, your partner Wannier function, when you calculate these matrix elements, might sit in a neighboring supercell, which is equivalent to say you consider the Wigner size supercell of a given Wannier functions when you look for the partner Wannier function, when you look for the Wannier function you want to calculate the matrix element with. Okay, and these are some numerical examples of why this is actually important, and especially in the case of gamma only sampling, but also more in general when you have coarse grids. Okay, so this is what is implemented in the code. Now this is the default format that is used, and just for you to know what is actually being calculated when you use Wannier interpolation. Okay? But I mentioned that the Hamiltonian is just one example, probably is the simplest example. There are many other operators that are lattice periodical that you can actually interpolate in the same way. So this is an example of spin. So this is the expectation value of the spin operator over block states in BCC iron, okay, and the color code represents the value of the spin. You see that now here in the lower side of this slide, I'm just substituting the H Hamiltonian with the X. X is one operator that is lattice periodical, and we do the same thing. Okay, so in this example of the picture, X is the spin operator, but it can be something different. Okay, so you represent it in terms of Wannier functions. You do this Fourier transform back in reciprocal space, and again, here for simplicity, I'm just using the simple formula. Remember that the correct way is through the minimal distance replica method, and finally, you just diagonalize your X operator, which is now again it has been interpolated in K-space. You diagonalize that to go from the Wannier gauge to the Hamiltonian gauge, and you get your interpolated quantity. Okay, so this is, I think, is a nice example of interpolation beyond simple band structures. Okay. Now we discussed at the beginning that there is a lot of freedom, no, in the way you calculate Wannier functions. There is this gauge freedom in the way you choose the unitary matrices, and the maximum localization procedure is a way to fix, to decide what is the gauges you want. Okay, but there are other choices. Okay, so one is actually to do nothing. Okay, so you just project onto some localized orbitals and you stop there. You don't do any iterative minimization. Then there is the major choice, the most popular choice, which is doing maximum localized Wannier functions. But then you can start to play with this minimization. So for instance, you can enforce some symmetries, okay, and do what are known as symmetry adapted Wannier functions, okay. Or you can decide that you only minimize the spread functional for some of the Wannier functions, okay. Or what you can do, and this is what constraint centers do, you can decide that some of the Wannier functions has to stay fixed in a specific position. Okay, the center has to be fixed. Okay, and so on. There are many other examples. I won't discuss all of them, of course. But if you're interested, these are covered in this review that I mentioned here in the bottom part of my slides. Okay, you can be also more creative. You can generalize the spread functional. One of these generalizations has been done by Feliciano, and it's called mixed Wannier block Wannier functions, where you also impose a constraint on the energy bandwidth. Okay, so you start to have some energy, spread term in your functional. Or what you can also do is to change algorithm, okay, or change the starting point of your minimization. Okay, so what you are going to see in the tutorial is the main strategy, which is select, as we said, atomic or hybrid orbitals. But there are other strategies. Okay, in particular, there's been an effort towards more automated strategies to choose the initial starting point. Some actually has been, are almost 10 years old by Mustafa and his colleagues in Berkeley. One of these has to do with the selected columns on the density matrix, which is what I'm going to see, and we have a optional exercise in the tutorial of today. And this SCDA method actually has been put forward by mathematicians, okay? And mathematicians have also introduced other techniques. One is this continuous block gauges, which essentially is a way to implement parallel transport. But I think the most successful approach, and I think what is really superior to most of these approaches here, is the projectability disentanglement coupled with the manifold remixing. And this is actually, I won't talk about this because Junfen Chao, who's the main author of this, will actually give you a dedicated lecture and tutorial on Saturday. Okay. So I mentioned symmetries, okay, because in this spread function, actually, if you minimize it in the maximally localized Wannier function procedure, essentially doesn't care about the symmetry. Okay? It just gives you the more localized Wannier function that you can get. But sometimes you want to actually have, enforce some symmetries. And one way to do this has been proposed by Sakuma, and it boils down to essentially adding constraints to these unitary matrices. Okay, so you take the symmetry operations and use them to constrain the symmetry properties of unitary matrix. Okay, this is interesting. Is not super straightforward to use. I mean, it requires some. It's more difficult to automate. But there are other approaches that are somehow simpler, but indirectly give you similar results in terms of symmetry. So one is the selectively localized Wannier function. So you only, as we said, you only localize a subset of your Wannier function. So you minimize the spread for a subset of them. And you can couple this with these constraint centers. Okay, so you add a penalty term in the spread functional so that it costs you energy if you want to move to have a solution where the centers of any functions are far away from your predefined centers. Okay, and these predefined centers could be, for instance, atomic positions. Okay, so you can force many functions to be sitting on specific atoms. Okay. Okay, so but why? I mentioned there's been a lot of efforts towards automating the construction of Wannier functions, but why do we need this? Because in practice, this is the most delicate aspects of getting Wannier functions. So the fact that the code, the users of the code have to specify initial projections is really the most delicate part of the procedure, because it requires, in principle, some chemical understanding of your system, also some experience in how you tune the parameters. So this has been the biggest challenge for new users for many years. It was very hard to automate. And if you look at the forum, these are the kinds of emails we were used to receive. Okay, so you see, how can I choose the projection for this material? I would like to do graphene. How can I get convergent functions? Should I use P states for arsenic and so on? And so one of the first approaches that tried to solve this was the selected column of density matrix, which I will discuss shortly. And as I said, the method of Junfeng that we will discuss on Saturday is a more sophisticated way to essentially solve this problem of specifying initial projection. Okay. So how does the CDM work? And so the idea is that you have you take a density matrix over your manifold. Let's say you have the valence band of an insulator. Okay, you want to do many functions for that. So if you take the one body density matrix, this is a projector and is exponentially localized, actually. Okay, so the columns of this projector, if you represent it on a real space grid, are localized. And it's a bit like considering delta like projections and doing the scalar product between the density matrix and these delta functions. Okay. So you have many columns, okay, one for each point in this grid, and they're localized. So it seems like a good thing, but the problem is that, and by the way, the fact that these are localized is just one of the many manifestations of the nearsightedness of the density matrix. Okay, so this is actually something we expect. Okay, so it's just the way the density matrix on an insulator is always behaves like this. So we have all these columns that are localized, but they're not orthogonal, okay? And so what you would like to have is take these columns and find n of them. So if you want to get n Wannier functions for n bands, you want n columns that are linearly independent and then would give you a localized basis set, okay? But if I pick n of these columns at random, of course, this will not work because they are linearly independent, okay? So you want to select the most representative columns, and these will be essentially the ones that have less overlap one with each other. And the SCDM is essentially just a linear algebra way to implement this. So you do this QRCP algorithm. It's just a linear, say, a matrix operation that is implemented in LAPACK. Okay, so there's a library to do that. And what in practice this does, it finds the most representative, so the most orthogonal columns in the density matrix. Okay, they are almost orthogonal, and so you do a final orthonormalization to force them to be really orthonormal. And you can, and what I've shown was done for let's say in real space or for a single K point, but you can generalize this for multiple K points. Okay. Now, if you have these methods, okay, so if you want to do disentanglement in a sense, you can generalize this by introducing a smearing. Okay, so an occupation function could be, for instance, the error function that you see here. And as long as this smearing function is actually smooth, again, your density matrix would decay rapidly in real space. Okay, so you do somehow the same thing, but the problem is that now you have a parameter. Okay, actually you have more than one parameter because you have to specify the parameters of this smearing function, okay? And a key concept that we discovered help you to solve the problem, so to automate even the choice of these parameters and make the SDM method fully automated, are projectabilities, okay? And projectabilities are essentially the overlap between the scalar product between your block states onto, again, this atomic orbital. So you see, even in the effort to get rid of the atomic orbitals and use linear algebra to actually find the initial gauge and the initial subspace, in the effort to automate that, these atomic orbitals, they come back from the window somehow, but in a much more simple way, because now we only care about the overall projection. So we take all the pseudoatomic orbitals that you have in the potential field, we project our block states on all of them, and we see, which are the states that have an overlap with atomic orbitals and which are the block states that do not have an overlap. And this way, with a fitting procedure, essentially, we decide what are the parameters of our occupation function, of our smearing function. Okay? And of course, you also have to set the number of Wannier function that you want to extract from your that you want to get. And what we do is very simple. So we take a number of Wannier functions that is equal to the number of these pseudoatomic orbitals. Okay. So now we have a recipe to essentially obtain Wannier function in a fully automated way, and this is actually validation of this for a simple material. You see that if you change this mu and sigma, that are the parameter of this smearing function, you get different spreads for your Wannier function, but also different qualities in the interpolation. Okay, so the plots here on the right hand side measure how much your band structure accurately reproduce your reference density function theory, in our case band structure. And our choices, as we show, that essentially is optimal in terms of accuracy and stability of the solution. Okay, so we have tested this with on some hundreds materials. This has been automated with AIDA, so there are automated workflows to use this. And we won't see AIDA workflows in the tutorial of today, but you will see there is an optional exercise number 4 that guides you through the concepts of SCDM, and you basically will do by hand what the workflows now can do for you, and you will see how the projectability can actually help you to essentially extract the parameters of this SCDM method and get Wannier functions and Wannier interpolation without specifying orbital projections in for your system. Okay, but I stress this is is available, but I think what Junfeng will show you on Saturday is probably an even better approach than this. Okay, so let's go back to the ecosystem. Now we have covered somehow the interpolation of operators, so Wannier interpolation of the band structure of the spin operator and other operators, and what can you actually do with that? We said there are all these different applications related to transport, variology, topological invariance, Electron-Phonon, and more. There are other applications that are not listed here, but these I think are the major ones. Of course, the key application of this school is Electron-Phonon, so I won't even discuss that. I will just show you this picture, as an introduction. So you get your band structure with quantum espresso and phonons and electron phonomatrix elements. When you're 90, you get Wannier functions and this unit rotation, and then you interpolate the Electron-Phonon matrix elements on ultra fine Q points and K point grid, and you go on with trying to calculate your property, or the property you're interested in. Could be superconductivity, could be mobility, and so on. And this will be covered in full detail. Now, what other examples I would like to share with you are related, for instance, to baryology. So these properties related to Berry phases that are really central in the description of the electronic properties of materials. And one is the polarization, which, as Nicola has said to you yesterday, is actually a Berry phase. So this is a Berry phase, and A here is the Berry connection. The polarization actually can be expressed as a sum of Wannier centers. Okay, there's really this strong connection between polarization and Wannier functions. But there are other examples more involved. One is the optical conductivity. You see that we have band eigenvalues, but again, we have this Berry connection that appears again. And another example would be anomalous conductivity, okay, where you have an integral of the Berry curvature omega And this Berry curvature is just the curve of the Berry connection, okay? So these are some of the examples. There are many, many other quantities, okay, like this, that can be efficiently calculated by, again, representing not only the Hamiltonian, but also the position operator, and in some cases, even other operators, on a basis of exponentially localized Wannier functions, okay? And so you might ask, why is this useful? I mean, why do I have to do this? And this picture, I think, will probably answer your question, because this is the Berry curvature calculated along high symmetry line. I think this should be higher on, I think. And you see that the Berry curvature has spikes. So if you integrate the Berry curvature to get the anomalous conductivity, the contributions are essentially very well localized in K-space, and there are, very difficult to sample. You need extra dense grids to sample these spikes, okay? Because they come from essentially avoided crossings, okay? So sometimes you have crossings, maybe the crossings are split by spin-orbit coupling, okay? And these small energy differences give you strong Berry curvatures, okay? This will be almost impossible to sample correctly if you were to do direct calculations, okay? So in this sense, Wannier function enable you to interpolate this on extra dense grids and calculate more accurately, or we'll say accurately, the integral of these very discontinuous quantities in the reciprocal space, okay? And as I mentioned, you can do some of these things in Wannier 90, but these days there are dedicated codes, like Wannier Berry is one of these, that focuses on the calculation of materials properties, in this case, Berry phases properties, through the use of Wannier functions, okay? Now, also topological invariants are, as I mentioned before, are very much related to Wannier function. Actually, the very definition of what is a topological insulator somehow is related to Wannier function. So topological insulators are systems that do not admit a Wannier representation. So you cannot construct Wannier functions for the valence bands of topological insulators unless you break any protecting symmetry of the topological phase. So if you topological phase has timer versus symmetry protecting the phase, you just can't get Wannier functions that are time reversal partners, essentially. Okay, and this has to do with if you want, the nature of topological insulators. There are systems that cannot really be mapped to their atomic limit without closing the gap. And the atomic limit would be the systems where you increase the distance within all the atoms, you explode the crystals until you get isolated atoms. Okay, so if you do this process in a topological insulator, you close the gap no matter how you do it. And this manifests as with the presence of these boundary modes that are protected by the topology. Okay, so if you want, topological insulators are systems deeply connected with the impossibility of having Wannier functions, but still Wannier functions enables to calculate topological invariants in topological insulators. And you use a very special type of Wannier function that's called hybrid or hermaphrodite Wannier function, which is Wannier just along one direction and is block-like along all the other directions. Okay, so in 2D, in 2 dimensions, for instance, this works like calculating the Wannier centers along x. This would be your polarization along x. And you do this as a function of ky. And you study as the centers, the sum of the centers, wind around the Brillouin zone as a function of ky. Okay, and the winding number of the center is essentially Chern number, which is the most fundamental topological invariance. Okay, and you can derive other topological invariants in the same way. And this has been done by Soluyanov and Vanderbilt. And if you're interested in these topics, there is a fantastic book by David Vanderbilt on the subject, which is called Berry Phases in Electronic Structure Theory. Okay, so now I move to a different kind of application that has been also discussed by Nicola yesterday very briefly. So spectral functions and spectral properties. Here we are trying to go beyond dense functional theory. And as I said, there are different ways actually you can do this. So one way is to go through Green's functions, and this will be covered in some of the lectures of the school. And this will be, for instance, what you do with GW and related methods. And you have diagrammatic approaches. So you use Feynman diagrams to calculate what is the self-energy and so on. Another approach is to instead choose a functional theory, a bit like DFT, but DFT is too simple to give you the spectrum. So it's just a static local theory, okay? And so if you could just have a functional theory that now maybe depends on the frequencies, okay? You could actually get a spectral theory. So one could calculate band structure from a functional theory, okay? And in the quasi-particle picture, this actually could mean that if you have a functional, not the frequency, but the orbital, so orbital density dependent functional, you might be able to calculate the spectrum of a material, okay? So the band structure of material, okay? And as Nicola has mentioned yesterday, one approach is through the Koopman's compliant function that essentially enforce piecewise linearity with respect to fractional occupations, okay? So DFT has a deviation from piecewise linearity, and the Koopman's function restores the right piecewise linearity, okay? And you can intuitively understand why you expect this. So if you have a fractional occupation, it's a bit like having a linear combination of systems with an integer occupation. So you really expect the energy to be linear with the fractional occupation, okay? And so the core ingredients are linearization. So you impose that this is piecewise linear, and then you take into account screening and relaxation effects, so that the orbitals actually relax once you populate them, so once you change their occupation, okay? What is interesting is that if you do this, you get a functional that, in the case of Koopman's, depends on the total charge density, also on the orbital charge density, that is not invariant under unitary rotations, okay? If you remember, we have already seen an object that was not invariant under unitary rotations, and this was actually the spread function, okay? In fact, the orbitals that minimize this functional there are covariation orbitals. These look a lot like Wannier functions, okay? So you can use maximum localized Wannier function as a proxy for the true variation orbitals that are different from the canonical orbitals, that are the ones that you get if you diagonalize your Hamiltonian, okay? And so recently, actually, with Nicola Colonna, what we did was to generalize this to non-collinear calculations. So now you have a function that depends not only on the orbital charge density, but also on the orbital spin magnetization density, okay? You can do a simple second-order Taylor expansion. You get your local Koopman's function, and it's a functional, as I said, of the charge density of any function, but also of the spin density of any function. You use this as a one-shot correction on top of density function theory, in a similar to what you do with GW in the one-shot G0 approach, okay? But the key aspect is that orbitals are maximal localized Wannier function, okay? And this is a bit the sketch of the theory. So you have a theory where you have the charge interaction kernel that comes from the T, charge spin interaction, spin interaction, and this is screened by the response function that also is charge spin, and spin, okay? And we discovered that actually the spin dependent interaction and screening effects are really important and crucial, but they totally miss in the most standard diagrammatic approaches, which instead are based on the random phase approximation, will essentially only give you the orange block here, so only the charge interaction, okay? And this actually gives you very accurate band gap. So this is a perovskite, okay, where spin-orbit coupling changes the gap by almost 1 electron volt. And this is a ferromagnetic insulator, chromium triodide, and you see the band gap that we get with this KCW method with spin-orbit coupling are in the same order, let's say in the same range of quasi-particle self-consistent GW with vertex correction, okay, which is much more costly and much more complex from the point of, I think, of the users probably, okay? So we have a very high accuracy with low computational cost and complexity, okay? And we think that this is because we have orbital and spin-dependent screening and interactions that are, in a many-body perturbation theory framework would be like enforcing vertex corrections, okay, that are much more actually complex to calculate. And this is going to be available in Quantum Espresso very soon, probably already in the last or on the following release, okay? And now I'm coming towards the end, so let's go back a bit to the code, and you have seen what is the status of the code as of today, but there are major updates for the code that are about to be released. One is the new 4.0 version of 90, where the code has been restructured and completely, and this is an effort led by Jerome Jackson and his colleagues from STFC in Daresbury in the UK. So essentially, the current code can be either used as a standalone code or as a library, but the library doesn't contain all the functionalities. The new version of the code will be essentially a library, and if you call the code as a standalone, this will essentially just be a wrapper of the library, okay? So, and the idea is that this will probably, facilitate people in using 90 as a library as opposed to a standalone code, which is the most popular way of using 90 as of today, okay? And this also comes with a very nice unified Python interface for 90 and for the I/O, okay? I mentioned that these things are discussed in a recent review that we have put together, and you see these are this is the long list of authors, and you can recognize some names that are instructors in the school. There is Roxana here, there is Junfeng, there is Nicola. We really have worked hard on this. Is a 56 review, 53 pages review, okay, and 15 pages are only of references. I think this is very useful for all newcomers to this field of Wannier functions, but also for experts, because we really have so many pointers to more in-depth and dedicated references for the different topics. And you find on the archive, and we will upload an updated version very soon. And hopefully this will, is under review mod fees, and we are confident that this will be published very soon. Okay, and this is the list of topics. You see, we really target the practitioner. Okay, so you see Wannier functions for the practitioner. There are tips on how you have to how to look at accuracy, how to look at convergence, and the focus is really on the codes of the ecosystem. So all the post-processing codes, one of these, of course, being APW, that enable you to calculate materials properties in different contexts. Okay, and now, of course, there's also a lot of educational material we have collected over the years, especially during the summer school. So this was the first summer school we did for the broader Wannier ecosystem, as opposed to the previous summer schools that were only for Wannier 90, and this was done in Trieste. And you find all the recordings and tutorials available on YouTube and on the ICT webpage. And there are more advanced topics than what I will cover in the hands-on tutorial of today. Okay, so if you're interested to learn how to do symmetry of Wannier functions, you might find actually a tutorial on the webpage of the school. And the same year, we also did a developer meeting. Okay, and so you can also find the lectures of this, on the talks, the recorded talks of this developer meeting. It's actually interesting because I found that some of these talks have been cited as reference in papers. So I guess there was a technical content that was particularly interesting for the community. Okay, and we try to do this developers meeting every year. So 2023, this was in the UK, in Dewsbury. This year we had it at the Paul Scherrer Institute in Switzerland, hosted by Nicola and Giovanni Pizzi. And if you're interested in developing features, just monitor this, because you might actually want to join us in one of these meetings in presence. Okay, and in these meetings we actually do useful things. Like in the last one, we came up with this ecosystem registry. This is a GitHub page that collects all the codes that are interfaced with Wannier 90. By now we have 53 codes that are listed, but we are sure there are many more. So every now and then I get a notification, an email that says, I have this code, it's interface with Wannier 90. And also for users, this is very, I think, relevant for you, because this is searchable. So you can find if there is a code that calculates the property you're interested in through Wannier functions. Okay, so I really encourage you to check this out. Okay, I'm almost done. This is a kind of my conclusion. So what are the trends, I think, for Wannier functions for the future? So we have seen the initial projections that used to be the bottleneck of the Wannierization are not a problem anymore. Many more applications are unlocked, and all these automated Wannierization methods come with a fully automated AIDA workflow. So this really should be it really should be easier now for users to use this to calculate Wannier functions, let's say, in a fully automated way without much effort. Okay, so one method is the SCDM method, and that is available in Quantum Express and Wannier 90. There is a more sophisticated method, which is projectability disentanglement and manifold remixing, will be discussed by Junfeng. And as I mentioned, we have extended this also to GW calculation. So you also find automated workflows to do Wannier interpolation of GW band structure. Okay. I think another trend is symmetries, in the sense that we have so much computational power, and now we can afford to have slightly more expensive K-point calculations if in exchange we can get more symmetric Wannier functions, especially for interpolation purposes. The SCDM method, I think, is a good case. You get a fully automated strategy, but the Wannier functions that you get are not symmetric. Okay, they don't look like nice atomic orbitals, and this, for a number of applications, is not very good. Okay, so in some cases you don't only care about the localization of a function, but you also want them to somehow have some of the symmetries that you expect in the crystal. Okay, and this is still not fully automated, but there are approaches like the one in Junfeng that actually indirectly do a very good job in getting more symmetric Wannier functions in an automated way. And finally, as I said, And Wannier 90 is becoming more and more as an engine and pure library, okay, of a reference implementation of Wannierization algorithms in Fortran, okay. While there is a growing number of packages in the ecosystem that are dedicated to calculate actual materials properties, okay. It could be, some optical conductivity, some mobility, some Berry curvatures, and some topological invariants, and more, okay. And now there are emerging codes like the one of Jean-Feng and Julia that can be used to experiment with new ideas and new methods before implementing, a more robust, having a more robust and reference implementation in Wannier 90, which still is the reference, if you want, library, okay. And as I said, also, we will use more and more this as a library as opposed to a standalone code, okay. Okay, just 2 slides about advertisement, and I'm done. First one, I'm organizing with Ion Herrera, Shubhana Narasimhan, and Gianmarco Milanese, the next edition of the Total Energy Enforced Methods workshop in Trieste, and this is probably one of the most important electronic structure workshop worldwide, which is held in Trieste since the 80s, every 2 years. We have really a great lineup of invited speakers, so I really encourage you to monitor the website k-mailing list and the ICP website, because we will soon probably open for applications, and also contribute abstracts, because we have reserved some slots for contributed abstracts to be upgraded to invited talks. Okay, so you might actually get an invited talk this way. And finally, I recently moved to CISA and created a small research group there. So we have postdoc positions, we have PhD position with industry and startups. So if you come to Trieste for the Total Energy and you like the place and would like to stay for a few more years, there are plenty of opportunities, and on different topics, from design, discovery of novel materials, spin-orbit coupling physics, machine learning methods for electronic structure simulations, topological materials, Wannier functions, and much more. And with this, I thank you for your attention. Sure.
Thank you very much. So we can have questions from the audience. This time we will try to use the mic so that the online audience can hear. Any questions?
Right. So when we talk about symmetry adapted Wannier functions, what kind of symmetries do we actually talk about? Is it like the spacebook symmetry or what?
Yeah. I think I have to. Okay, I have to use this one. Let me go back to. Yeah. Okay, so you have a symmetry operation, G, okay, and you use the representation of your symmetry operator is a crystalline symmetry. So yes, it has to do with the space group of your crystal, and you can choose actually which symmetry operation. Of course, it has to be a symmetry of the system, but you can choose which ones you can enforce, and you use the matrix representation to change, if you want to, the unitary matrix U such that this is compliant with the symmetry. Okay.
Sometimes it's useful to have, like, we have non-commutative operators. We simultaneously localize them. There's no eigenstate that exists. Can you construct maximally localized functions?
When you have what exactly?
Operators that don't commute.
Yeah.
So they don't have eigenstates that simultaneously diagonalize them, but can construct maximally localized functions as locally as you can.
But let's say, I'm not sure I understood the question. So if you have a manifold of states, you can construct Wannier function for the manifold of states. Now, of course, in one dimension, this is like diagonalizing the operator PXP, where X is the position operator. In 2 or 3 dimensions, you cannot simultaneously diagonalize PXP, PYP, and PZP. So you have to do a iterative minimization, as we discussed. So yeah, I mean, as long as you have a manifold of block states, and you can always try to get your Wannier representation. I don't know if this is.
You mentioned the spin example.
Yeah.
You said it like doesn't have to be the Hamiltonian, or doesn't have to be the Cauchy operator.
Yeah.
Any operator that you can localize.
Yeah, it's an operator that has to be Lattice periodical, so it has to be something that is a function of k. Okay, So H of K, F of K, S of K, like this. You can do that separately. So you can interpolate Sx, you can interpolate Sy, you can interpolate Sz. There's nothing that prevents you. As long as you can calculate. So let's say you have an operator. As long as you can calculate that, as the expectation value among block states, you can. And this is K local, so it depends just on K, or as the spin, it doesn't even depend on K itself. It's you can do that.
In slide 12, you have selected some of the bands in the carbon chain. How do you project the bands within the subfold of the band? Yeah.
So this has to do with the disentanglement procedure. So you here choose p orbitals, okay, and if you look at the equation we discussed here, so you project, okay, on these p orbitals, and then you minimize the spillage between neighboring manifolds, okay, after you have projected on these p orbitals. So what the code does is select the states, if you want, that are represented by p orbitals, that project more on p orbitals. And the point is that these states are not ordered in energy. So the band number 5 here around X might be represented by p orbitals, but as you move along towards gamma, you don't just go for the lowest lying state, you just go up here. So these states are more free electron-like, these gray states here, while this one here is more is actually made of p orbitals. So which is the reason why you can follow this by minimizing. So you mix the states in order to minimize the spillage from one K point and the other, and you follow the band with the right orbital character, which in this case is p orbitals. Okay.
Thank you. We'll take one question from the online audience.
So the question that I want to give after Wannierization, how much Wannier spread is accepted? Because sometimes that's quite fine. However, the calculated band structure matches well with the calculated band structure. How can you conclude the Wannierization?
So I think, so first of all, the spread is extensive. So you have to normalize that by the number of Wannier functions you have to, if you want to compare different materials. Okay, this is the first aspect. And then I don't think there is a general rule. So what you can do is to compare the gauge invariant part and the gauge dependent part. Of course, you want a gauge invariant part that is not much larger. It's probably should be smaller than the gauge independent part. And then I think you should compare orders of magnitude. Okay, it's very hard to give say a general rule of thumb, but it's true that the interpolation quality is actually a measure of how good your organization is, because if your spread is too large, you will need very, very dense K-point grid to get converge, and so I think interpolation is one way to actually check if